Hello and welcome back to Calculus, the series where we explore rates of change, areas, and volumes. First, I'd like to thank all the nice people that support this channel by liking and subscribing. It helps a lot in order for me to make more videos for you in the future to enjoy. Now, as promised, today we will be looking into limits. Limits in calculus are used to describe the behavior of functions, or to be precise, the behavior of specific points on the graph. Putting the definition in words would be what happens to a function's output as its input approaches a specific value. The output simply means the y value and the input means the x value. If this definition is extremely wordy, then let's start with an example. Let's say we have a function given by f of x equals to x plus 2. And we want to know what happens to the output of this function as x approaches the value 1. We denote this with an arrow pointing from x to the number 1. To understand this better, let's immediately visualize this on a graph. The point x could be anywhere on a graph. However, as it slowly approaches x equals to 1, you can see that the corresponding y value would get closer to 3, which in this case is the correct answer. And so the formal notation we use is this. We write lim as x approaches 1 on the bottom of the function x plus 2. And the answer would be equal to 3. It is not always as simple as that. So let's take a look at another example. Let's say you want to find the limit as x approaches 2 of the function 1 over x minus 2. As you can see, here you can't simply just take the limit value and plug it into the function. Simply because then we would get 1 over 2 minus 2, which is equal to 0, and that is impossible to calculate. It is also why if we were to visualize this graph, there would be an asymptote at x equals to 2. So what exactly happens here as x approaches 2? In this case, we can actually evaluate the limit from two directions, from the left-hand side and from the right-hand side, simply because our graph exists on both sides of the vertical asymptote. Let's begin with the left-hand side. The notation we use remains the same, just with an additional minus sign on top of the 2, which denotes that we're evaluating the limit from the left-hand side. To see what happens, here we can pick numbers less than 2, however, numbers that are also arbitrarily close to 2. For example, x equals to 1.9. If we were to put 1.9 into our function, we would simply get 1 divided by negative 0.1, which is indeed equal to negative 10. Let's say now we pick another x value that is even closer to 2. In this case, 1.999. Here, plugging the value in, we will simply get 1 divided by negative 0.001, which is equal to negative 1,000. If we repeat this process for numbers arbitrarily close to 2 from the left-hand side, we will simply get larger and larger corresponding outputs, or in other words, larger negative outputs. So now, the correct question to ask would be, what if our function does not settle at a finite number? What if the limit is not a finite number? With this example, we could see that our corresponding outputs were closely approaching negative infinity, which is mathematically undefined. This is because infinity has different sizes, some of which are completely incomprehensible. Thus, we put the infinity symbol as a substitute, but the limit itself is still considered to be undefined. The same thing works from the right-hand side. If we were to pick x values arbitrarily close to 2 from the right-hand side, we would simply approach the number or undefined symbol, positive infinity. Once again, it is still undefined. The infinity symbol is simply a substitute. Now that we have a grasp of the basic concept of limits, let's look at a few examples. For the first example, they are asking us to evaluate the limit as x approaches 3 of the function x plus 2 over x minus 2. This one is quite simple. We can simply plug in the numbers into the function and we get 3 plus 2 over 3 minus 2, which is equal to 5. Okay, now let's look at a more complicated example. We are asked to evaluate the limit as x approaches 2 of the function x squared minus 4 over x squared minus 2x. Here, we cannot simply plug in the number 2, because then our denominator would be equal to 0, and division by 0 is not possible. Thus, we have to look how to simplify this function. We can see that the top part can simply be rewritten with difference of squares, as x minus 2 times x plus 2. And on the bottom, we can just factor out an x, and we would have left x minus 2 in the parentheses. Now you can probably see there is x minus 2 in both the numerator and the denominator, which means we can simply cancel them out. So now we have simplified it to limit as x approaches 2 of the function x plus 2 over x. And now plugging in 2, we would simply get 4 divided by 2, which is equal to 2. Lastly, let's look at a more difficult example. This time, our x will not approach a specific value, but it will approach positive infinity. And our function will be given by negative x squared plus x plus 2 divided by 3x squared plus 2x minus 1. Here, the limit looks pretty complicated. However, there is a simple trick that we can employ. This would be dividing every single term by x to the greatest power, in this case, the power 2. We do this because of a simple fact about limits as x approaches infinity. If we are asked to evaluate the limit as x approaches to infinity of any number divided by x to any power, this limit will always be equal to 0. So here, in our function, we get limit as x approaches infinity of negative 1 plus 1 over x plus 2 over x squared divided by 3 plus 2 over x minus 1 over x squared. Here you can see 4 of these terms correspond to the rule of x approaches infinity. It means the corresponding y value will simply approach 0. So basically what we have left is limit as x approaches infinity of negative 1 divided by 3. And since negative 1 over 3 does not have any x value, the answer here would simply be 1 over 3, negative 1 over 3. Finally, to go a little bit off topic, we can look at an application of limits outside of calculus. If you have ever done series and sequences, you have probably heard of the words converging series or converging sequence. It simply means there is a sequence of numbers and they get arbitrarily small and converge to a certain value. It's also where this rule comes from. If you want to learn more about that, check out my series about series and sequences. All right, now that you know what limits are and how to calculate them, we can easily move on to derivatives in the next video. So I hope to see you there and have a nice day. Bye.